product pooling or universal design. So the next type of pooling that we will consider is called product pooling, sometimes also called universal design. Consider this a stylized example where we have two related products, P1 and P2, and we replace them with one product of universal design, P, right? So we have P1 and P2, replace it with some universal design P. So the idea is that we create a product P that serves the demand, satisfies completely satisfactory the demand for product P1 and P2. Let's say you have a product that has features of both, and right, and we can basically we can convince all customers for P1 and P2 that they can as well buy product P. So we're going to consider here a seasonal product, right? Like we had in the topic on the news vendor model. And so suppose we have these demands for those two products identically distributed, normally distributed with mean 3,192 and standard deviation 1,181. If those demands for the products P1 and P2 are independent, then demand again for product P, the combined one, will be on average 2 times the mean of individual products, and standard deviation, because of independence, will be square root of 2 times the standard deviation, right? So again, if you assume those products have identical price, cost, and salvage value, this is for simplicity in our stylized example, right? The cost of underage will be 20, the cost of overage 80, critical ratio 0.8, whether it's for a single product or for both products, right? So from that, we can calculate the performance of ordering those two products individually, right? Each of them, as we determined in the news vendor model topic, we had to order 4,196 to maximize profit. So if you manage them separately, you have 2 times that amount of inventory ordered, and expected profit will be 2 times the expected profit from a single product, P1, either P1 or P2, identical, right? So this is going to be the expected profit from the two products. However, if you consider the performance of the universal design, the product P, the quantity you need to order is smaller than the 2 times 4,196 here, right? And if you calculate expected profit, it's going to be also larger this time. So notice that we have benefits in both dimensions in terms of inventory investment, right? We order less inventory by about 7%, and yet the profit increases by about 4.4%. Of course, our analysis depends on how correlated the demands for product P1 and P2 are. And what we assumed in the previous calculation is that they are uncorrelated, right? So they have independent demands. So this would be the case shown here in this figure, right? Where rho, or the correlation coefficient, equals 0, correlation between demands for product P1 and product P2. So basically they behave independently. They can be both high, they can be both low, but one of them could be low and the other high, or the other way around, right? However, we might have products that are highly positively correlated, like in this figure, in the lower figure here. And in that case, the benefit from pooling wouldn't be as high, because when one has higher demand, the other also has high demand. And when this one has low demand, right, one product is here on the horizontal axis, the other is on the vertical axis. These are some products with much smaller demands that we're considering, mean 10 and standard deviation 3, right? If one of them has small demand, the other is also usually has a similar small demand. So when products are correlated positively, there won't be as much benefit, right? Actually, the most benefit we will experience when correlation is negative, in this case here, right? When you have one demand for one product is high, the other is low, and the other way around, when this demand is low, the other product has high demand. So the key driver of product pooling is demand correlation for those products. And in general, when you look at two random variables, x and y, where x has some mean mu x and standard deviation mu sigma x, and y also has mu y and sigma y, mean and standard deviation, then if you add those two random variables, like we combine the demands, right? So we add those demands together. We have the mean equal to the sum of the means. And the standard deviation is actually a more complex formula. This is calculating the square of standard deviation of x and y, which is actually called variance. It's the sum of the variance for the variable x, variance of the variable y, and 2 times the product of standard deviations and the parameter rho being the correlation. Rho xy is correlation between variables x and y. So let me show you how you can get from these calculations for mu and sigma of the combined demand to the relationship of the coefficient of variation of the universal design, how it depends on the coefficient of variation for single product. So assume that we have those products P1 in P2, right? P2, they are both normally distributed. Each of them has mean mu and standard deviation sigma. And let's assume now that the product, the universal design P, has mean, let's call it mu P and sigma P, right? So because we know the combined mean should be the sum of means, we basically can say that mu P is equal 2 times mu. It's mu plus mu, and those products, remember, are identically distributed in our stylized example. But what happens to the sigma P? What is sigma P? So because there is a square here, I'm going to consider that this is a square root of something, right? And then I will write this formula, this right-hand side here, as right, sigma x and sigma y are both the same now, the same sigmas, right? So they are basically sigma squared plus another sigma squared, right? And then this is plus 2 times, and then sigma times sigma, and it will be again sigma squared, and times rho, right? So the rho will be now the correlation, remember, between those two products, right? Rho, let's put it on the side here, right? The rho is correlation between the demands of P1 and P2. So to further rewrite this, of course, right, we have 2 sigma squares and another 2 rho sigma squares. So this is 2 plus 2 rho, 2 rho. So that will be 2 rho. And then sigma square, we can take it outside of the root and just write times sigma, right? So now if I want coefficient of variation for my initial product, CV, right, for those products, CV is just sigma over mu. Now CVP for this combined product, right, this product P, will be, of course, sigma P over mu P. And I can continue the calculation by plugging in. For mu P, I have 2 mu. So in the denominator, I'll have 2 times mu, right? This is the formula. And then for sigma P, I will plug in this. So that will be square root of 2 plus 2 rho square multiplied by the sigma here, right? And notice I have here, right? I have here this mu, sigma divided by mu, which I know is the CV of the initial product. So I can continue the calculation here by putting something times CV, right? This is going to be just CV, right? This part, right? But what is square root of 2 plus, square root of 2 plus 2 rho divided by 2? Now, if you want this 2 to go under the square root, you have to basically divide under the square root by 4, right? So we will have square root of, right, 2 and, right, so this 4, we can replace it as square root. So this 2, I replace as square root of 4, right? And then that means it's 2 divided by 4. I'm going to keep it as 1 plus rho divided by 2, right? So I had divided by 4, but I have 2 and 2 here. So I can simplify it to 1 plus rho without the 2's, and then this divided by 2, that the denominator here remains just 2. And this is, as I said, multiplied by the blue part, that's multiplied by CV. So the key here to see is that coefficient of variation of the combined demand will be related to the coefficient of variation of individual products. Remember, they are identical products, right? By this multiplier. And then the thing to see here is that rho, right? This parameter rho, it can be perfectly negatively correlated, or it could be the demands could be independent, they are uncorrelated, or perfectly positively correlated. These are the three extreme kind of values. So this is an extreme, this is an extreme, this is a mid value, right? And this is what we want to consider. So going back to my slide here, I explained just a moment ago that coefficient of variation for the pooled demand of this universal product, when we have two identical products, P1, P2, coefficient of variation will be coefficient of variation of one of those products, right? Either of them, they have identical coefficients of variations because they are identically distributed, right? But multiplied by this parameter that depends on rho, and rho is the correlation between product P1 and P2 demands. So we can consider what happens if demands are independent. Just plug in 0 here for rho, right? And it will be 1 plus 0 divided by 2. So that will be half under square root, or if you like, this will be as if we divide by square root of 2, right? And so the coefficient of variation for the pooled demand compared to individual products will be decreased by some, by dividing by some number around 1.41, right? If you have positively correlated products, rho is 1, plug in 1 here, and you have 1 plus 1, that's 2, divided by 2, that's 1, and square root of 1 will be 1, and so coefficient of variation of pooled demand will be the same as coefficient of variation of individual demands. And so in this example, you actually don't get any benefit, because if there is no decrease in variability, the inventory that we need is exactly the same to satisfy demand of universal design. And when you have negatively correlated products, perfectly negatively correlated products, the CV of the pooled demand becomes 0, because plug in here -1, right? And you get 1 minus 1, that's 0, divided by 2, still 0, square root, still 0. So you have 0 times this, and so 0 times whatever is still 0. So CV of pooled demand is 0. Of course, this is a very stylized example, remember. The CV of the pooled demand wouldn't be 0 in practice, because those two products, P1, P2, wouldn't have identical distribution of demands. And rarely in real life, we have also correlation exactly equal to -1, so perfectly negatively correlated demands. But it tells you that the CV of the pooled demand will be very low, much lower than the case of independent demands for those products, right? So if you have negative correlation, the CV will be decreased most. So basically, product pooling is most effective when the CV of the universal product is smaller than CV of individual products, right? It is the case in the independent demand. It is the case in the negatively correlated demands. It will not be the case if demands are positively correlated, right? So, and especially, the reduction um, in the CV will be especially great if we have negative correlation, total negative correlation being the extreme value here. So is product pooling or universal design a solution to all our problems? Of course it isn't. The reason for that is creating a universal design is not that easy, right? You might actually have customers who have significantly different needs, and you might have a cost increase if you create universal design. So basically, you have to be careful how you pool the demand. If you have some key functionality for some customers with special needs. An example is bicycles. You can't just create a bicycle that will satisfy everyone. You either have thick tires or thin tires for different terrain, right? And you have different steering for mountain bike and different for fast road bike, right? So it's actually probably very hard and not impossible to create a universal bicycle for all customers, right? As I said, it can be more expensive to have all the functionalities in one product, right? Although it might be less expensive to procure because you have economies of scale. You have 2, 3, 4 times the demand of individual products if you pull, create a universal design of multiple products from multiple products. Also, the problem could be that it eliminates brand price segmentation opportunities, right? This is why, for example, Toyota has Lexus brand, right? Because they want to have a more expensive, luxurious model, right? And they want the customers to be proud of owning Lexus and not just a Toyota brand, even though this is the same company, in fact, right? So if you want different prices to cater to different segments, even for example, if quality is actually similar, you might need this differentiation, so you cannot go for a universal design. However, notice that if excessive product differentiation from the perspective of this analysis, that merely divides fixed customer base, right? So if you have a product and then you create two variants of that product and you really don't gain any demand from this, right? You don't increase the sales and you don't have higher demand, right? That is actually counterproductive. So it is important to consider some kind of product rationalization, product line rationalization, right? And a lot of companies have a lot of variants of the products, this gets out of hand, and that actually creates an increased cost of matching supply with demand, while without actually benefiting us in terms of, for example, increased sales.